I'm representing the Department of Building Services and Engineering from the Technical University of Iasi in Romania. The subject for today is a geothermal heat exchanger with special geometry. I will explain everything when we get there. So, in the usual technical solutions, geothermal heat exchangers are made with one or more horizontal pipes or vertical pipes, also having a constant diameter that ranges between 32 and 45 millimeters of the junction points at the heat pump or at the distribution collector. So the transfer heat flux varies along the pipes, causing uneven stress of the massive soil. By realizing heat exchangers with variable geometry consisting of insulated modules that have transfer surfaces in an inverse ratio proportional to the average working agent temperature, we can uniformize the thermal fields and ensure a balanced loading of massive mass by homogenizing the thermal density and reducing the surface of lands and length of the drillings. At the Department of Building Services Engineering, we have conceived the geothermal heat exchanger with variable geometry. It consists in a series of concentric registers with variable numbers of copper or stainless pipes with constant diameter and increasing transfer surface. The connection of the registers is made alternatively in order to realize their countercurrent flow and compensate the thermal flows along the pipes. According to the real heat exchanger, the physical one is five times smaller and has the following characteristics. The external diameter is 15 millimeters, the internal one is 13 on the upper and lower rings. The vertical pipes have a diameter of 6 millimeters on the exterior, on the interior it's 5 millimeters, the height is 50 centimeters, and the external diameter of the entire heat exchanger is 36.5 centimeters. It has 3 registers with 8, 16, and 24 vertical pipes, such as we can see in the image. This is the actual heat exchanger that we use, and it has been tested in our laboratory. The dimensioning is done by applying the equation of balance and thermal transfer, and it involves determining the number of pipes of each register, the density of thermal load throughout the storage volume for the imposed conditions, the dimensional structures, the thermal load, and the extreme temperatures. The thermohydraulic regime, determined by the flow velocity of the heat exchanger agent through pipes and by the global coefficient of heat transfer, varies along the exchanger from one register to another. In this slide, I have presented the equation that define each parameter used in the calculation of the heat exchanger. As I said, the heat exchanger has been tested inside the laboratory. It was part of my doctoral dissertation, and we have very good results that include the density, the load of the mass of the soil, because it was used in a soil, and as a working agent fluid, we have used water. We want to extend our research by using as a working agent nanofluid with variable concentrations. Thank you for your attention. Yes, I have them. It's on my laptop. I can present to, yes, it's in my thesis. My thesis was presented in September, and there are Excel tables, charts made there with the results, and they are pretty good, actually, yeah. Yes, we have imposed some conditions, which is the velocity and the temperatures. So we had 3 temperatures with 3 velocities. So we had 9 cases that we've studied, and the best one, with the better results, there was the one in the middle with 40 degrees Celsius and 0.9 meters per second velocity. That was the better case. So, thank you. Yeah.
I will ask the question this way. Oh, thank you. Hello, kindly please. You have forced convection inside, you have forced convection outside, or free convection?
It's free convection.
Free, okay. Nevertheless, my question would be, if from thermal point of view, I don't speak about the economic or energetic aspects. You can compare your heat exchanger with a normal plate heat exchanger used normally in district heating or domestic hot water, and if you can explain your advantages in using this
type of heat exchanger.
Yes, with free convection outside. We have used such heat exchangers for solar systems, for the accumulator using water glycol inside for the winter. But may I confess, in the 80s, the results were not fantastic because of the very low alpha coefficient on the free convection side. So it's my experience in the old times. And I'd try to help using maybe some other kind of heat exchangers with horizontal pipes, maybe, not vertical. Thank you so much, but it's a very interesting research. And even if a research will demonstrate that something is not really very efficient now, the result is good because we will no more follow this path.
Okay.
Okay, thank you so much.
Thank you. You want me to explain it now, or we can talk after? Explain it now?
Yes, if there is a comparison with a plate heat exchanger in our mind.
So the main idea that we had when we conceived this heat exchanger was to uniformize the load of the soil. If I can you open the PowerPoint, please? Thank you. Okay. Okay. So the agent is coming through here, and it's going downstairs. It fills the first ring, which goes up, fills the second one, goes down, fills the third one. The idea was that making this heat exchanger with this geometry and the number of pipes that are proportionally growing is because the temperature that goes inside in the first place is higher. And as soon as it travels the heat exchanger, it will go lower. And this is why we had to think about another type of heat exchanger so that we don't have the same problems as the normal ones. We have tried to study a plain one, as the one you mentioned. Unfortunately, we weren't able to group the entire plates that we had there. It was a much complicated process, and we didn't have the possibilities to do it. But we will think about it, and we will study it in the future. We also have another heat exchanger with another geometry variable, which is tested on water as a tank, in a tank.
Thank you very much.
Thank you.
This to Professor Novak.
Yeah.
Because the question was the very important one. You need forced convection, both sides.
Okay. Thank you.